Part C of the question is a capacitor question. Figure 5.5 shows a circuit for charging a capacitor and then discharging it through a resistor by use of a 2-position switch. Figure 5.6 is a graph of the variation of charge Q in the capacitor with time during discharge. And as usual, that Q graph is an exponential graph. And I'm just going to write down the equation here. And you'll remember that equation. Q is equal to Q naught, e to the minus t over CR. So the first part of the question says, state how you would use figure 5.6 to obtain an accurate value for the time constant of the resistor capacitor circuit. So the time constant is the time that has passed when the value of Q has fallen to 37% or 1 over E of its original value. So you would have to calculate Q equals 0.37 Q naught. Draw a line across from this value to the curve and then down to x-axis. And that will give you your value of t, and then you would repeat that again for 0.37 of 0.37 Q naught. So do it for a second time. So I'll just show you what I mean here. So say your 0.37 is here, right there. That's 0.37 of Q naught, and that's CR. But you could repeat that again for 0.37 of this. And then that second value there is CR as well. And then you could take the two values and add them together and divide by 2. So repeat this and calculate average time. The resistor in figure 5.5 is replaced with one of a greater resistance. The process of charge and discharge is repeated. Sketch a graph on figure 5.6 to show the new variation of charge Q with time Q with time T. So this time R is much greater. That means if R is much greater, then tau is greater. So therefore you're going to draw in a curve which is less steep. And I just put in a different colour here, so you can see on your graph here. Starting at the same value, but just not as steep. And you have to label it, no, it doesn't say you have to label it. We'll call it number 2 anyway. Graphs are also much used in the analysis of experimental results. Starting from the fact that many principal relationships that you might investigate experimentally may be put into the standard form y equals mx plus c. Give 4 reasons why a graphical treatment of results is such an advantage. Well, the first advantage is that, first of all, you can calculate a gradient and hence some kind of constant from the graph. You can also calculate an intercept value, and that's that constant c from the graph where the line crosses the y-axis. You can draw a best fit line, and your best fit line is an average of your results. You can clearly see any anomalous results and leave them out if that the case may be. So they can be left out of best fit line. So any 4 out of 5 there will get you your marks. There's 1, 2, there's actually 2 marks there and 1 mark there. So any 4 out